Okay, so we've seen how valence bond theory, what it is, how it just involves the overlap of atomic orbitals with singly occupied orbitals to form bonds. How we can use that to explain some of the observed characteristics of molecules. So valence bond theory is useful up to a point, just like Lewis theory was useful up to a point. We still need to invoke some more concepts in order to understand some other observed phenomena. So for instance, if we know, for example, that in carbon dioxide, so in CO2, you draw the Lewis structure for it, and this has been experimentally determined as well, we know that the bond angle here in CO2 is 180 degrees. It's a straight line. However, based on what we just talked about in valence bond theory, if we were to look at the orbital diagram or the electron configuration for carbon, so carbon is 1s2, 2s2, 2p2. And if we were to draw our orbital diagram, we have our 1s, we have our 2s, we have our 2p. Okay, so 1s2, 2s2, and then our 2p, which has two electrons in each of um, the p orbitals. Based on what we just talked about in valence bond theory, this carbon atom here would have singly occupied p orbitals. So we would have, for example, a p electron over here and a p electron over there. And as we just said, the bond angle between both of these two is 90 degrees. So if I had an oxygen, I'm sorry, yes, an oxygen over here with one unpaired electron. Okay, we'll do this in a different color. If this is my O with its overlapping orbital, with its one unpaired electron, and another O over here with its one unpaired electron, we would predict that the bond angle in CO to actually be 90 degrees. Okay, but it is not 90 degrees. It is actually 180 degrees. So just basic valence bond theory does not explain this. Similarly, if we look, for example, in the case of beryllium chloride, BeCl2, we know that the valence electrons in beryllium are the 2s2 electrons. Well, this doesn't have unpaired electrons. How can it follow what we just talked about with valence bond theory? So one suggestion is that we can actually promote or excite, for instance, one of these electrons. We can promote it to the 2p sublevel to go into one of the 2p orbitals. And when it does that, well, then we have these two unpaired electrons. We have the electron in a 2s orbital, which again, the s orbital is spherical, would have one unpaired electron there. And then we'd have an unpaired electron in a p orbital, which has that hourglass shape like so. So we can imagine then around the beryllium, the Be, we can imagine that the overlap that can occur between the beryllium, which is going to have, let's say, an s orbital on one side, like so, and a p orbital on the other side. We'll just draw the like this on the other side with this one electron and one electron. And if I have the fluorines now that are coming in with their p electrons, they can overlap like this. So one fluorine over here with this unpaired electron, and then another fluorine on this side with its one unpaired electron. Okay, so the bonding here then is in the shaded region. Okay, what we can see is that on one side of the beryllium, where this s orbital was, we have an overlap between an s orbital on the beryllium and a p orbital in the fluorine. Whereas on the other side, we have the overlap of a p orbital in beryllium and a p orbital in fluorine as well. And those two are not the same, right? The overlap here is not the same as the overlap there, which means the bond length on both sides of the beryllium between the Be and the F in both cases, right? These would actually be different in length if this were the case. Okay, because the overlap between a p orbital and an s orbital, this overlap here, is not the same length as the overlap between a p orbital and another p orbital. So even though we can explain why it forms two bonds by promoting one of these unpaired electrons into a empty p orbital, it doesn't explain what the observed bond lengths are. Right? The observed is that the bond lengths, the Be and the F bond lengths, right? These are identical in length. So why does that happen? Well, this leads to something new, which is an extension of valence bond theory, which is known as hybridization of the orbitals. Okay, so we're looking now at orbital hybridization to explain the observed characteristics of our atoms or molecules, for example. And hybridization just simply means mixing. Okay, so in the case of, we just talked about experimentally, right, in our BeCl2, sorry, did I say fluorine before? I meant chlorine. The idea is the same. In the case of BeCl2, what has been experimentally determined is that the length of these BeCl bonds are the same, and the strength of those bonds are the same as well. So we could not have a one electron in an s orbital. We couldn't have another electron in the p orbital. They had those unpaired electrons had to be in the same type of orbital. And the way that happens is as follows. The two electrons that are in the 2s, we promote one of them into the 2p, and then what happens is we hybridize or we mix that s orbital with the p orbital. So what we do is we mix two orbitals, okay, which are an s and one of the p orbitals, and what we get out are two hybrid orbitals, which we call sp orbitals. Okay, we mix one s and one p orbital. That's why we call it an s and p, or sp hybridization. And now these sp hybridized orbitals, they are identical to each other, and they each are going to contain one of those unpaired electrons. So if I mix, this is the s orbital, the 2s orbital, this is the 2p orbital, I get out now two sp orbitals, which we'll zoom in a little bit here. They kind of look like a hybrid between those two, right? So it doesn't look like a regular p orbital where both lobes are the same. We have one that has a bigger lobe and a smaller lobe on one side, and the other one has a bigger lobe on the other side and a smaller lobe on the other side. This is an sp orbital. That's the other sp orbital. We have two of them that are identical to each other. And each of those electrons now, those unpaired electrons, they are in each of these orbitals. This then would explain why with the beryllium at the center, right, it can now overlap with the p orbitals from the chlorine or the fluorine, for example. So this is my Be here in the middle. Okay, now I have my one of the sp hybridized orbitals on one side, and then on the other side I have my other sp hybridized orbital, like so, each with one electron. And then I have my regular p orbital from, let's see, a chlorine. That's like this. Okay, it has one electron in it and another chlorine over here. Okay, with its one unpaired electron. There's the overlap. Okay, and the bond distance here okay, is the same in both of these, right? So this is the P and that's the P. So the hybridization then explains the experimentally observed features of, in this case, BeCl2, but it applies to lots of other instances as well. Right, so there's the beryllium with the S and the P. It's hybridized. Now the green one here, this is the green one is the hybridized sp orbital. This is the sp, and that's the sp hybridized orbital. It can now overlap um, with the p orbitals. Now, because we have two of them, right? They're going to be opposite to each other to be as far apart from each other as possible. They will overlap with the p orbitals in chlorine, for example. Right there, you see our overlap. I'll draw the electrons in so we can see one electron in and another one. These are from the beryllium, and then the chlorines each can bring their own. Put those in green in each of those cases. Right, that's how, again, we're basing the bonds forming on overlapping of orbitals, but which orbitals now, right? So we have to have promotion of an electron to make it unpaired, and then hybridizing or mixing the orbitals to provide the correct number of orbitals that explains the bonding that we actually observe. So that's orbital hybridization, or hybridization of atomic orbitals to provide these hybridized orbitals. Let's take a look at another example. And we'll do a very common molecule, one simple molecule that we've seen, we've looked at before. Let's take a look at, we'll do, let's do CH4, which is methane. Okay, so experimentally, we can, or not experimentally, but we've drawn the Lewis structure for methane before, CH4. It has this sort of tetrahedral shape, right, based on Vesper theory. Right, this is our correct Lewis structure for it as well. Let's talk about now how this actually forms according to valence bond theory and hybridization of the atomic orbitals to find or to determine the shape of the molecule and the types of hybridized orbitals involved. So in the case of carbon, carbon is our central atom. So we know carbon is 1s2, 2s2, 2p2, right? So there's our 2 electrons in the 2s. There's our 2 electrons in the 2p sublevel. What we need in order for carbon, right? Carbon has 4 bonds in the structure, which means that there needs to be 4 unpaired electrons in order for it to form 4 bonds. Okay, in our case here, we only have 2 unpaired electrons. So just based on what we know about orbital overlap and having unpaired electrons, just based on this ground state electron orbital diagram, carbon can only form 2 bonds because it only has 2 unpaired electrons. But that is not what we have observed. Obviously, carbon actually likes to form 4 bonds. And in order to do that, we need to promote one of these electrons, this one, for example, from the 2s into that empty 2p orbital. So now we have 4 unpaired electrons after promotion. Okay, now the other thing that we need to do, because we've noticed that there are 4 electron domains around our carbon, we actually need 4 of these hybridized orbitals, whatever they are, right? You look at your number of electron domains. Okay, so, and this is a general rule when it comes to hybridization. Look at the number of electron domains. This is the number of hybrid orbitals necessary. Okay, so I have 1, 2, 3, 4 electron domains. I need 4 hybrid orbitals. So when I promote this 1 electron here into the 2p, I have one s orbital and I have three p orbitals. These are not hybridized orbitals. I still need to hybridize these, which means I need to mix them. Okay, because in the case of CH4, all of these are equivalent to each other. Whereas here, right, they're not equivalent. We have an s and three p orbitals. So we're going to mix, we're going to hybridize one s orbital and three p orbitals. Okay, so we mix an s and three p orbitals. What we end up with is sp3 hybridization. Okay, so we put in a total of 4 orbitals in. Okay, and this is very important when you start hybridizing. The number of orbitals you put in should equal the number of orbitals that you put out or that you get out. So we get 4 sp3 hybrid orbitals out. Okay, we put 4 of them in, an s and 3 p's, so we get 4 sp3 hybridized orbitals. In order for these orbitals to be as far apart from each other as possible, right, the sp3 then must be 109.5 degrees apart, okay, and that is the tetrahedral shape. Okay, so when we talked about drawing Lewis structures and determining shapes and stuff early on, this now comes back to this hybridization and the fact that electron groups, right, want to be as far apart from each other as possible to stabilize or to minimize the repulsions between them. Again, stability is a driving force, which adopts that tetrahedral shape. Okay, so these hybridized orbitals, we mix an s and three of the p orbitals. The shape of the hybridized orbitals is a hybrid of those. So again, we'll find the hybrid orbitals looking a little asymmetrical. So we'll have a big lobe and then a small lobe, right? That's one sp3. We have another one, a big lobe and a small lobe. We have another one over here, a big lobe and a small lobe. We have another one, a big lobe and a small lobe. Okay, these are all sp3, 4 of them, and each of them has an electron in it now. Got 1, 2, 3, and 4. So what can happen, this is my carbon in the middle, okay, with its sp3, 4 of them, hybridized orbital, bond angle here, right, is 109.5 all the way around. If I have hydrogens around that have their s orbital with a single electron in it, they can come in and they can bring that electron in. There's my hydrogen. There's one valence electron. And they pair up because they're opposite spins. So another one. And that's how we end up now with our CH4. Okay, I'm shading in again the overlap according to valence bond theory. That's the shape of the CH4 molecule, which is a tetrahedron. Your book obviously does a much better job of depicting the diagrams. They're professionals at doing the art and whatnot, but this is how it looks if you were to draw it, for example, how the overlapping occurs between the s orbital and hydrogen with this one unpaired electron, that's the orange one, and then the 4 sp3 hybrid orbitals in carbon, right? We need to have those orbitals be identical because all of the carbon-hydrogen bonds are identical as well. We make them identical by promoting and then by mixing the s and the 3p orbitals to give us these equivalent sp3 hybridized orbitals, right? These are degenerate, okay, meaning they are equivalent in energy. We saw that term before. So let's take a look at another example. We've seen already hybridization of the s and p orbitals. What about if we bring maybe the other orbitals next in line, which are the d orbitals, into question? So let's take a look at an example. We have phosphorus pentachloride PCl5, and we want to use valence bond theory to explain the bonding seen in PCl5. So first thing we want to do, we have our Lewis structure, and then we want to count the number of electron domains around the the PC, the central atom, right? So around phosphorus, we have 1, 2, 3, 4, 5 electron domains, right? So remember the number of electron domains, well, the number of electron groups is equal to the number of hybrid orbitals that are needed. Okay, so we need 5. If we have 5 electron domains, we need 5 hybrid orbitals that are needed. The next thing we need to do is to take a look at that central atom phosphorus and write out the electron configuration and draw the orbital diagram for it. So phosphorus, the full electron configuration for P is 1s2, 2s2, 2p6, 3s2, 3p3. Okay, that gets us the phosphorus. So we draw the ground state orbital diagram for that central atom. And we just, again, all we need to do is focus on the valence electrons, which would be these over here. So we have our 3s with 2 electrons in it. We have our 3p, right? We have 3 of those p orbitals, and we have 1, 2, 3. Okay, so right now, according to our ground state, phosphorus can only possibly form one, oops, one, do that again. 3 bonds because there are only 3 unpaired electrons. Obviously, that is not the case because why would we have PCl5, right? It's able to form 5 bonds. So what we would need to do, okay, is we would first of all need to promote an electron to maximize the number of unpaired electrons. So right now we have 3 unpaired electrons. We need to promote this one. Well, we can't promote it to a P because they're all half filled. Well, the next available would be the 3D. And because we are in the third row of the periodic table, the third energy level, we do have those 5 d orbitals to select from. So we have 1, 2, 3, 4, 5. We promote this one up here. Okay, so we take that one away. And then we have our 5. Now, if we count them, 5 unpaired electrons. 1, 2, 3, 4, and 5. Okay, so we maximize the number of unpaired electrons by promotion. The next thing we need to do is then to hybridize or to mix them. So if I mix these, I'm going to mix an S, 3 of the P's, and 1 of the D orbitals. Okay, so I'm mixing 1 S orbital, I'm mixing 3 P orbitals, and I'm mixing 1 D orbital. So I'm mixing an S, 3 P's, and a D orbital. So I end up with sp3d hybridization. Okay, and if I put a total of 3, 4, 5 in, okay, I'm going to get 5 of these sp3d orbitals out. So we put 5 of these orbitals in, an S, 3 P's, and 1 D orbital. We get 5 of them out. And the 5 that we get out are hybridized sp3 orbitals that are all equivalent to each other. So there are 5 hybridized orbitals that each have 1 electron in them, which then would mean then that our P can form 5 equivalent types of bonds. Okay, so as you can imagine, the sp3d hybridized orbitals are just a combination of all 3 of them in terms of their shape. And their shape is going to look a little convoluted, right? You have, again, sort of like a big lobe and a small lobe, and you have 5 of these in this entire structure here, each with 1 electron in each of the hybridized orbitals that can then overlap with or share with another p orbital, for example, from the chlorine. So we have an electron in each of these, like so. Okay, and then we have our chlorine coming in and bringing an electron, its unpaired electron in the p. And it's p orbital, right? So the orange ones here are the phosphorus, and then let's do the purple ones are the chlorines that are pairing up. Okay, and the shape, in order for those orbitals to be as far apart from each other as possible, will be that trigonal bipyramidal shape. Okay, so those are the steps involved when we try to rationalize, when we try to explain the Lewis structures that we've seen previously according to Vesper theory. We can use the hybridization and orbital overlap to explain those observed geometries and observed bonding. So as a general rule of thumb, this is a really good table uh, to refer to as you're looking at determining the hybridization around any central atom. Really, all you need to do is to look at the number of electron domains on that central atom. And right away, we can tell the type of hybridization that is going to happen. So for instance, if you have two uh, domains around that central atom, and again, the electron domain could be, just remember this, the electron domain could be any of the following. It can be a single bond, it could be a double bond, it could be a triple bond, or it could be a lone pair. Any of these counts as one electron domain or one electron group. So if your central atom has two electron groups around it, there's sp hybridization, right? And you count the number of orbitals, that's the number of electron groups that you have. sp, two hybridized orbitals, two electron domains. We have three electron domains, sp2. We have four electron domains, sp3, because we have three p orbitals and one s orbital. Now, when you get to 5 and 6, we have to now start using the d orbitals to hybridize, because you'll have a maximum of three p orbitals, right? So next in line would be the d. So five electron domains would be sp3d, and if you have six electron domains around the central atom, well, then you need another d orbital, so it'll be sp3d2 for the hybridization involved. And again, here you'd have six of these hybridized orbitals for the sp3d2. The shape there obviously is going to be octahedral compared to the trigonal bipyramidal, tetrahedral, trigonal planar, and linear for the ones that came before it. Okay, so we've invoked hybridization to explain the bonding, the observed bonding and geometries in different molecules. And we've so far looked at instances where there were only single bonds, but what about when there are double bonds or multiple bonds, either double or triple bonds? We can still use valence bond theory and the hybridization of atomic orbitals to also describe instances where molecules contain either double or triple bonds. And we'll take a look, first of all, at the case of ethylene, C2H4. If you draw the Lewis structure for this, you'll see that there's a double bond between the carbons, H is on the outside. And then here we have our central atom with three electron groups around it. Okay, so we would expect a trigonal planar geometry around these, each of the carbons around here. What we would expect, because we have three electron groups, okay, based on the table before, let's go up back to the table. Three electron groups around the central atom, we would expect sp2 hybridization. All right, so that means we need to hybridize an s and two of the p orbitals. So first thing we need to do, however, for carbon, because that's the central atom in both cases, we need to first of all promote an electron to maximize the number of unpaired electrons. So we move that one up. We end up now with single electron in each of these, the s and the p. And now we need to hybridize it such that we end up with sp2. So we would want to mix an s and two of the p orbitals. Okay, not all of them, because that would be sp3, just two of them. So we mix an s and two of the p. We end up with, we put three orbitals in. Okay, we get three orbitals out. Three of the hybridized orbitals in. I'm sorry, three regular orbitals in. We get three of the hybrid orbitals out, which are the sp2, each with one electron in them. Okay, so we have a remaining electron that is in that remaining 2p orbital that we didn't hybridize. This is an unhybridized p orbital that's left over, right? We didn't mix that in with the others. So that's on its own. And that unhybridized orbital is the orbital when it overlaps with other ones that gives rise to either the second bond in a double bond or the second and third bond that you'd find in a triple bond, right? So what actually happens in both of these cases? Well, this gives rise to different types of bonds that we're going to see now. So the two types of bonds that we're going to encounter, and two types of overlaps, really, two types of orbital overlaps that give rise to two types of bonds. So the first one is called a head-to-head overlap. And that's my term for it, head-to-head overlap. And this gives rise to a type of bond called a sigma bond. The symbol for sigma is like a 0 with a tail there at the top. Okay, and this is the most efficient type of overlapping. And it's efficient or best overlap because the shared electron density actually lies directly along or between the nuclei. So that's known as the internuclear axis, right? So for instance, if you have a, the hybridization in two of the carbons above, well, we have our three hybridized sp2 orbitals. We'll highlight these in green and we'll kind of do a dotted line around these. That's one of the hybridized orbital, a second one, and this is a third one. And remember, this is happening on the other carbon as well, right? So when these two here overlap head to head, so this one and that one, okay, head to head overlap, like here, okay, that gives rise to the sigma bond, right? We have an electron in each of these. Okay, so now they're this is very efficient overlapping that is happening. So in other words, it's a strong overlap, a strong type of bond. Okay, that's a sigma bond, head-to-head overlap between the atomic orbitals. Now, what's left over, you can probably see on our diagram here, is the carbons now. We have the hybridized orbitals, the other two hybridized orbitals with their one electron each in them. Okay, they can overlap with hydrogens within their 1s and their 1s orbitals, like so. And those would be sigma bonds as well, because in the spherical shape of the s orbital, we would have that occurring. So it's head-to-head overlap there as well. These will be sigma bonds. Sigma bond there, and another sigma bond over here. This is a sigma bond there as well. Okay, sigma bonds over on this side as well. So what you also see is that we have these leftover p orbitals, right? They have the characteristic p shaped, which is the figure of 8 or the hourglass shape. And these can overlap as well with each other, but they overlap side to side like this, both above and below the plane. Okay, so this is known as a side-to-side overlap. And that is not as efficient as a head-to-head overlap. Okay, and when you have that side-to-side overlap of the p, of the unhybridized p orbitals, that gives rise to a different type of bond. So this is not as efficient. That gives rise to a bond called a pi bond, pi, and this is the symbol for pi. And that's the second bond in the double bond, right? So the double bond is made up of the The sigma bond, that's always the first bond that you see. And then if there's a double or triple, the pi bonds make up the remaining types of bonds. Okay, so I think your book, again, does a good job of illustrating that in a way that's a little bit easier to visualize than I drew it. So apologize for the moving back and forth. Okay, so here you can see an actual shape now of the remaining p orbital. So again, it's a little bit more spread out here on the top and on the bottom. That's your p orbital, unhybridized p orbital on one carbon. And then the other one hybridized like, I'm sorry, unhybridized like this. And you can see the overlap there on the top and the bottom is there's not as much overlap as in a head-to-head sigma bond, so that it's not as efficient. And you actually have two lobes, one on top, one on the bottom. Both of them together make up a pi bond, right? So this overlap above and below is what the pi bond is. And that happens a lot when we have, any remaining unhybridized p orbitals overlapping in that sideways fashion to form that pi bond. So if you have a structure and you had to identify the number of sigma bonds and pi bonds in that actual structure, there's a quick way to determine this. So if we have uh, our structure here, whenever you see a single bond, if it's just a single bond, it will be a sigma bond. Okay, so single bonds are sigma. Double bonds are made up of two types of bonds. We have a sigma, that's the first bond that you see, and a pi bond. So we can count the number of single bonds that we have. We'll highlight those in yellow. So we have a single bond there. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, let me double check that and ask or look at what the question is actually asking. The question's asking for the number of carbon to carbon sigma bonds. Okay, so it's really important that you read the question, and this is a good reminder of that. We're looking at carbon-carbon sigma bonds, and then the total number of pi bonds in thalidomide. Right? Thalidomide was a drug used in the 1950s to relieve people from morning sickness, but then it was found out that it actually caused birth defects, so it was discontinued. So let's actually start with the simplest one first here, which is a number of pi bonds. Okay, so pi bonds are only going to be found in double bonds, so we can highlight those, the double bonds in pink. So we have 1, 2, 3, 4, 5, 6, and then 7, right? So we'll have 7 pi bonds. And then we want carbon to carbon sigma bonds. Okay, so let's write out where the carbons are. We have a carbon, 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 all the way around. Wherever you don't see a nitrogen, carbon is understood to be in these structures. So we'll draw those in. So we'll highlight the carbon-carbon sigma bonds, which are just the single bonds in green. So we have one here. That's 1. There's 2. There's 3. Carbon-carbon 4. 5, 6. There's 7, 8. In the double bond, there's 1 there, 9. There's 10. There's 11. And where else do we see? I think we're missing one. And then one in the middle here, 12. Right, so you have a total of 12 carbon-carbon single bonds, which are sigma bonds. And then we have 7 of the pi bonds in this particular structure. Okay, so again, single bonds are typically your sigma bonds. Double bonds are made up of two types. The first one is a sigma, and then the second one will be a pi. If you had a triple bond somewhere, Okay, a triple bond will be made up of sigma, and you'll have two pi bonds in there, because we have, in a triple bond, you'll have two unhybridized p orbitals that can both overlap to form pi bonds. Okay, so one of the ramifications of the different types of bonds is whether or not the bonds can actually, or the atoms can rotate around the bond axis. And what we find, what we observe is that in a sigma bond, which again, these are single bonds, there is free rotation around the bond axis, meaning the atoms can rotate around. So wherever you have a carbon-carbon single, right, this bond can rotate around, this bond can rotate around, that bond can rotate around if you needed to, right? So it's not like they're locked in place. There's actually free rotation around single bonds. That is different than if you had a double bond present, right? Double bonds, and specifically now the presence of the pi bond restricts that free rotation around the bond axis, which means the atoms are locked in place. Wherever they are in the molecule, they are locked in place. They are not free to rotate around. So for instance, in this molecule here, we have, and remember, when you have a double bond, the shape there is trigonal planar, right, around both of these carbons. The H and the Cl, right, one's on one side, one's on the other side. Those are locked in place. The H and Cl on the other side, those are locked in place as well. There's no free rotation around those two. They cannot move back and forth like they would around the single bond. So as a result, we actually have two possibilities of this molecule, even though they're made up of the same formulas. They have different structures because of the restriction of free rotation. We refer to these types of situations as isomers. Okay, and that's present. It could be possible when we have these carbon-carbon double bonds, which result from the side-to-side overlap of the unhybridized p orbitals, which are the pi bonds. They restrict rotation around that part of the molecule. Okay, so the last one that we'll take a look at here in the hybridization is when we have a triple bonds. So for instance, if we have the molecule acetylene, which is used in welding and in other applications, if you draw the Lewis structure for acetylene, which has a chemical formula C2H2, you will see that there's a triple bond right in the middle between both of the carbons. So now we can actually look and say the types of bonds that we have in this, and we'll talk about how it happens in a second. So we have a single bond here. Okay, that's going to be a sigma bond. We have a single bond there. That is going to be a single bond. We have a triple bond in the middle, and the triple bond is made up of a sigma. And then we have two pi bonds that make up that triple bond. All right, so the same type of thing we can apply when it comes to determining the hybridization and the overlap, etc. So we have carbons. We need to maximize the number of unpaired electron. We're going to promote that electron to make it unpaired. And then we're going to hybridize the requisite number of orbitals so that we end up with, in the case of the carbon here, right, we have two electron domains around it, so we need to hybridize two orbitals. We're going to mix an s and one of the p in order to get our requisite hybridization. So we're going to see sp hybrid orbitals, right? So we put two orbitals in, an s and a p. We get two sp hybridized orbitals out. Okay, so we end up with these two sp hybridized orbitals. What you will notice also is that we have two p orbitals, two of the p orbitals that are unhybridized. Which is going to be important when it comes to the bonding. All right, so we have our, let's show in now our hybridized orbitals and other orbitals around each of the carbons. Okay, so the green ones here, the hybridized orbitals, we have let's see, we can draw these electrons in. The one on the left, we have this is our sp. We have another sp over here, an sp here, and another sp. Then the blue ones are just a regular p orbitals, right? So this is a p orbital, and then this is a p orbital there as well. Each of these, if you look at our thing here, each is going to have one electron in them. Okay, so let's draw those in, try to color code it. So the red ones are on the left carbon. So one, and then that's in the other p. This is the p, sp, and then sp. Okay, and then the one on the right, we'll do that one in do purple maybe. Okay, so we have the one electron in each of the orbitals. So one here in the sp, another one in the sp on the other side, and then in each of the unhybridized p orbitals. So when these come together, right, we have our overlapping in the middle here. So this is that's the sigma bond. Okay, head-to-head overlap with the sp, hybridized sp orbitals in the middle. And then now the unhybridized p orbitals, okay, they can overlap in a side to side, or we'll usually draw lines to show this. And I'll try to highlight these in color here. So we have this overlap, side to side overlap of this p orbital. Remember, this is happening both above and below. Right, so that's one. Everything in yellow here is one of the pi bond, which is the overlap of the p orbitals. And then we have another set of p orbitals that can overlap. This goes perpendicular now in pink, right? So that's happening on one lobe. It's happening on the other lobe here as well. Okay, so for a total now, and we'll try to highlight these, this here is a pi bond, and then in pink here, that's another pi bond. So in between the carbons, we have that triple bond made up of a sigma and two pi bonds. Sometimes, you don't see this term used very often, but sometimes the pi bonds, because when we draw them, they kind of look like bananas. Sometimes they're called banana bonds. And you'll see that in the internet and elsewhere. Because that's the way that we can illustrate, how the bonding is happening. It really is a little bit more complicated than that, but that's one way to kind of help you remember what's happening. So in acetylene, right, you actually have electron density between both of the carbons in the middle, made up of the sigma bond, head-to-head overlap of the hybridized sp orbitals, and then two pi bonds made up of the side-to-side overlap of the unhybridized p orbitals. Keep in mind now, the side-to-side overlap is not as efficient, so the pi bond is inherently weaker than the sigma bond. So like, for example, a double bond is actually not twice as strong as a single bond because that second part of the bond, the pi bond, is a little bit weaker. So it's not necessarily double the strength of a single. Similarly, a triple bond is not triple the strength of a single. It's less than that because the pi bonds are inherently weaker.